Hey guys, happy Friday. This is a AP problem from the year 2004, really similar to the ones we did in class, except that it also includes finding a second derivative. And I know that was the lesson that some of the kids who were, sorry about that, that some of the two kids who were at home missed. And so I wanted to do this problem just so you would have some notes on finding the second derivative. All right, finding this first derivative in part A is really similar to the problems we did in class. All right, so we're starting off, these are those joyous times when College Board tells us what we are supposed to get as our answer, and we simply have to find it. So this is just finding the dy dx, so I'm going to take the derivative here. And on the left-hand side of the equation, there's nothing special that I have to do other than remembering that when I take the derivative of the y, I need to write a y prime. On the right-hand side of the equation, I need to remember to use the product rule on that piece there. The derivative of 7 is just 0, but the derivative of 3x times y is 3x y prime plus 3 times y. Now it's just a matter of collecting terms. So I'm going to bring the 2x over to the other side. That's my 3y minus 2x. And then I'm going to go ahead and bring my 8y prime, keep that there, and bring over the 3xy prime. Factor out my y prime, and now I have shown what they want me to show. That's a lovely skill that they're asking. They're asking me basically to parrot what they have already said, and I'm happy to do so. That's actually worth 2 points on your AP exam, and you'll have to do that on your quiz this week. For part B, you're going to show that there's a point P with an x-coordinate of 3 at which the tangent line is horizontal. This is actually easier than the problems that we did together in class. If the tangent line is horizontal, hopefully you understand that that means that dy dx must equal 0. For dy dx to equal 0, it must mean that 3y minus 2x must equal 0. That's my numerator from the dy dx. That's my numerator from the dy dx. Now, it's just simply a matter of saying, I want to figure out if there is a value that works for this that will also work in the initial curve. Remember, this value has to fall on that initial curve that we were given way up here. All right? All of the values that I find, anything that has this characteristic also has to fall on the curve. It has to lie on the curve. When we solve 3y minus 2 times 3, I'm letting that x equal 3. I'm trying to find that there's a point P with an x-coordinate of 3. So I'm going to let the x equal 3. That means that my y value has to equal 2. So does this point lie on the curve? That's my potential time when x is equal to 3. In order to show that it has a tangent line at x is equal to 3, specifically at 3, 2, I need to show that 3, 2 is on the curve. To do that, I'm simply going to plug in here. I'm going to do 3 squared plus 4 times 2 squared, and I'm asking myself, does that equal 7 plus 3 times 3 times 2? And here it does. This is 25, and it does indeed equal 25. So that means that 3, 2 does indeed lie on the curve, and that because 3, 2 also yields a derivative, the derivative at 3, 2 is 0, that means that this curve has a horizontal tangent line at 3, 2. Okay, finally we have to find the value of the second derivative. So I'll slow up a little bit for this part. For us to find the second derivative, obviously we're going to look back at the first derivative. So here's my first derivative here. And what we're going to do is we're going to be taking the derivative of that. Oftentimes, especially in the context of an AP exam, but even in just a lot of problems that you might see, even in the multiple choice or in any part of this year, oftentimes we have to use the quotient rule in order to get dy dx. To get d2y dx squared, our second derivative. We're going to use implicit differentiation yet again. We already used it back in part A, and now we're simply going to use it again. So let's go ahead and do that. Please note, by the way, I'm sorry, I should have mentioned this. In this problem, if you tried to do this problem on your own, this question is asking, does the curve have a local max, a local min, or neither? That's not a question that you are able to answer yet. In a month from now or so, about a month from now, you'll be able to answer that rather easily. But for now, we're just going to find the value of d2y dx squared at 3, 2. So first, let's find that second derivative. So we're going to use the quotient rule here. This works the same way as when we did implicit differentiation to find the first derivative, just with one fundamental difference. So it's going to be the bottom times the derivative of the top. The derivative of the top here is 3y prime minus 2 minus the top times the derivative of the bottom. And the derivative of the bottom here is 8y prime minus 3. And all of this is going to be over 8y minus 3x squared. We're trying to find this thing at a point, at a value. And so this question can be asked in different ways, but in this we're just trying to find the value at a point. In some problems you might actually have to go ahead and plug in your first derivative into the second derivative. Remember, you solved this y prime back in part A of this problem. And in order to get to the second derivative, you would have already found y prime. So sometimes you might just be asked to plug in the dy dx wherever it says y prime or just dy dx in the second derivative. Here, though, you have a little bit of an advantage because you know what dy dx or what y prime is at the point 3, 2. You found that in part B. In part B, we saw that dy dx at 3, 2 is equal to 0. So wherever I see, when I do my plugging in into this, wherever I see a y prime, I'm just going to write 0. This is going to become 8 times our y value is 2 minus 3 times 3 times 3 times, and our y prime is 0 there. Again, I can write 3 times 2 minus 2 times 3. Again, the y prime is going to be 0. I'm going to write a 0 in there, minus 3. At this point, it's just testing your math, like your numerical skills. It's not even calculus at this point. Okay, so that's a little bit of a pain to solve by hand, but I guess we can do it. That's 16 minus 9 is 7. 3 times 0 is 0, times a minus 2 is negative 2. All right, then we're going to subtract. 3 times 2 is 6, minus 6. Oh, this whole second part, isn't that delightful? That whole second part is just going to go to 0. So down here we have 16 minus 9, so that's a 49. So that's 7 squared. And we're left with negative 14 over 49. Okay? So, very briefly, I just wanted to do one more problem finding the second derivative of using implicit differentiation. So let us find, where is this problem I was going to do for you guys? Okay, here's the second problem I thought I would do. Let's find y double prime by implicit differentiation. And let's do it with x to the third plus y to the third is equal to 1. So when I do this, what do I have to do here? Well, my first step is just to find dy dx. In order to get to y double prime, I've got to get to y prime. So this is 3x squared, 3x squared plus 3y squared is equal to 0. Oh no, what did I do wrong? Well, if you've been paying attention, I forgot to use the chain rule. All right, so the chain rule here would require me to have a 3y squared. That's right, y prime is equal to, what's the derivative of 1? It is 0. So this y prime, all right, well, we'll show all the steps here. So the 3y squared times y prime is equal to negative 3x squared, and y prime is equal to negative 3x squared over 3y squared, or negative x squared over y squared. But the problem is asking us to get y double prime, isn't it? So let's go ahead and find y double prime. As I mentioned before, usually y double prime is found by using the quotient rule. So let's go ahead and do that. Y double prime is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom. The derivative of the bottom here is going to be 2y, y prime. That whole thing is going to be over the bottom squared. So we have to associate this negative sign, by the way, with either the bottom or the top. It doesn't matter which, but I just decided to kind of have it hang on to that negative x squared. So we did the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And now we can just simplify this thing as much as we can. So this is going to become negative 2x y squared. And this over here is going to be plus 2x squared y. And now, instead of writing my y prime is the same thing I solved for over here. This is y prime, isn't it? So when I rewrite this thing, especially if this is a multiple choice question, the answer is going to require that I rewrite in terms of just x and y. So this is going to be 2x squared y times negative x squared over y squared. That whole thing is going to be over y to the 4th. We could certainly leave this problem like this for now. But I guess, if you want, you can just clean it up a little bit. I don't know what you want to do to clean this up. It's not exactly the most glorious thing I've ever seen in my life. But, I don't know. I guess we could cancel out a y there. So this is negative 2x y squared plus, and that's going to be, that should become a minus. 2x to the 4th over y, and all of that over y to the 4th. It would probably be just good practice for us to write this as 2xy squared over y to the 4th minus 2x to the 4th over y to the 5th. All right, all I did there is divide both by y to the 4th, and 2x to the 4th over y divided by y to the 4th would give me that y to the 5th in the denominator. And then if I just want to simplify just a little bit more, this is negative 2x over y squared minus 2x to the 4th over y to the 5th. The big thing with simplifying is that you stay flexible while simplifying, because you only have to simplify if it is a multiple choice question. And so if it's a multiple choice question, you've just got to simplify until you figure out that it matches with one of the answers that is already there. Okay? I hope you all have a wonderful weekend. Thank you for watching. Goodbye.